we have the function is xy divided by x squared plus y squared. And the question, does this limit exist? Well, as I did in the previous example, I'm going to try a different path. And the first one will be, we'll set y equals 0. And we check, so we approach the limit along the x-axis. All right, so in this case, we have the limit is of x comma 0 approaches 0, 0. And because y equals 0, then we have x times 0 divided by x squared plus 0 squared. Well, that's obviously 0. So it takes no time to do it. And now the next thing we'll do is we'll set x equals 0. In other words, we approach the limit along the y-axis. And the limit, this time we have 0y approaches 0, 0. And we'll do the same thing. So we have 0 times y divided by 0 squared plus y. Once again, it's 0. So far it looks good. We try one way, we try the other way, and we arrive to 0 both times. Okay? So here's the thing that I want to warn you, and that's the reason for this exercise. Checking the approach or approaches, the approach along the x and y axis is insufficient. To show existence. Perhaps no, you spell it P-A, right? I'm sorry? P-E-R or P-A-R? Yeah, I missed the R. Perhaps there is a different approach will give a different value. A third approach gives a different value. Okay, so what we'll do, we'll try, we'll set, this will be the third approach, we set y equal x, okay? So we approach along the line y equal x. So what do we have? The limit, we write it because y is x, we're going to write it x comma x. Approaches 0, 0. And instead of x times y, we'll have x times x divided by x squared plus x squared, right? And this will be x squared divided by 2x squared. So, so it's the limit is x approaches 0, 0. There is more to write here, but it's x squared divided by 2x squared, and that's obviously equals 1/2. Now 1/2 is different than 0. So the limit does not exist. Uh, no, infinitely many is sufficient. It's sufficient to show one that is different. All it takes is one case where you have a different value to disprove. But to prove, you need to use a theory, or you need to use the precise definition, the delta epsilon definition. So you guess a value of L, the limit, and you say, okay, let's guess L equals 0. And can you find for every random, arbitrary small value of epsilon, can you find a suitable delta? If you can, then the limit exists. I'll show you an example where you're going to use the squeeze theory. Okay. That's basically the same question Warren asked, and let me write the answer to this question. Okay, what we're going to say is we're going to say that it is only required to show a single occurrence where the limit value is different to conclude that the limit does not exist. So to answer your question, really, all it takes is one to show that it doesn't exist. But your question is how the heck we know how we prove that the limit exists. And I already said it twice. One way is to use the precise definition. The other way is to use one of the theorems that we learn in Calculus 1, and they apply also in this case. And the next example will show you how we're going to use the squeeze theorem for example, to show that the limit exists. All right?